Okay, this video will be about particle physics, and so the thing is that I have notes, so I'll be looking at my notes. So the thing is that Einstein proved that atoms existed with the random walk formula for Paulin and Brownian motion. So he proved that atoms exist. And so the thing is that when he came up with this formula, it was the beginning of quantum mechanics. But quantum mechanics was actually invented in the 1860s by the person who came up with entropy, I think. And so the thing is that Einstein came up with it in 1905, that he proved that atoms existed. And so the thing is that most people think that there's this thing called a Bohr diagram of the atom. And so people think that the atom is like a little ball that balls that stick together and bounce off each other, but that's not what it is. You see, there's this thing called the quantum field, and you see the smallest possible measurement there is called the Planck's constant, and the Planck's constant is 10 to the negative 33 centimeters. That's 33 zeros worth of small things, and when you cube that number, you get 99 zeros worth of Planck lengths inside that area, inside that volume. And so the thing is that an atom is not empty space. An atom is like a fluid of electrons, a fluid of electromagnetic waves, and so we only call them particles because when we measure them, we have to bounce things off of them to see how small they are. So we're actually concentrating we're concentrating all around one area, and when we concentrate around that area, we're trying, like the Large Hadron Collider, we put things together and then we collect all the things that pop off of the explosion of the collisions. And so the thing is that there's these things called quantum fields, and these things are very, very small. Like I said, 99 zeros within a cubic centimeter. And so the thing is that these things, they vibrate. So the thing is that according to the Standard Model, there's at least about 12 or 13, I don't know how many. There's several particles in the Standard Model, but the thing is that they're not really particles, they're networks. So the thing is that in string theory, they have these little strings and they're vibrating, they're rotating, and they're going back and forth and they're whizzing about. But the thing is that that's not really what's happening. What's happening is that there's a network there's these they're not really strings, because they're not elastic. They're not infinitely elastic like in string theory. What happens is they're discrete. They're finite, and so space-time is discrete. Particles are discrete. Quantum physics has everything in discrete forms. And the thing is, that's one of the reasons why quantum physics and general relativity has trouble being merged together, is because everything in general relativity is infinitely fluid, and everything in quantum mechanics is discrete in chunks, and these chunks can't be divided. That's why it has quantum, because quantum means indivisible. Atom means indivisible in Greek. And so the thing is that so when Stephen Hawking was thinking about black holes, he said that that the singularity does not exist. Singularities do not exist. Black holes exist, but they aren't singularities. Information cannot be destroyed when they go into a black hole. Now, he thought that black holes were two-dimensional. That once you go into the black hole, it reflected back into itself, and it came back into the universe from the outside. So you go into a black hole, and you go on the edge of the universe, and you go back inside. And so that's a fourth-dimensional view of how a black hole works when you merge four dimensions with two dimensions. But the thing is that in quantum physics, what I personally think is that everything is five-dimensional. So the thing is, in the multiverse theory, there's an infinite amount of particles, or there's an infinite amount of worlds. But the thing is that the reason why they have these infinite amount of worlds is because there's an infinite amount of ways you can combine strings together. So the thing is, strings are, like I said, infinitely elastic, and that's not true because everything's discrete in quantum physics. So everything being discrete means that strings cannot be infinitely elastic. And because they're not infinitely elastic, you can have combinations of things together. But the thing is, like, so the multiverse theory says there's 10 to the power of 500. So 500 zeros of the amount of combinations you can create with strings. But the thing is that's just some people think that, okay, so there's a universe, a universe, a universe, a universe, and they're all next to each other. But the thing is that that's not how it works. What happens is there's branches, and these branches are not in the third dimension. These branches are not in the fourth dimension. These branches are in the fifth dimension. And when you and so the thing is that when you think about where is a particle going to go, so a particle can go is in the third dimension. You have a particle here, and it can go in any direction it wants. And where is it going to end up? And so the thing is that there's this thing called symmetry breaking. And so you have to break symmetry in order for a particle to go from one place to another place. And so the thing is that when you calculate all the possibilities of where it's going to go here, then here, then here, and here. And once you add up all the steps of where the particle is going to go over time, it branches out into the fifth dimension. And also, it's the fifth dimension. When you do these branches, it's not only the one particle doing the branching of all the possibilities it could go like that, it's also all the other particles interacting with each other, and this creates a five-dimensional object of all possible worlds, or all possible branches. But the thing is that we do not live in that kind of world, because it's sort of like if you had all possible computer programs. Now, all possible computer programs can exist in possibility space, but it can't exist on a computer. So a computer can create three-dimensional virtual reality in three-dimensional, but the thing is, it's just a linear line. It has 1 to a billion in a Windows 98 computer. That's why it's 32-bit. And a 64-bit is not a billion. It's a billion times a billion to the billionth power. It's a billion is 9 zeros. 64-bit is 18 zeros. So you can't have infinite amount of of all possible computer programs on your computer at the same time, depending on the length of that program. So you can create an object, and that object can be so let's say that we have 10 to the 90th power of atoms in the universe. Now, if we were to put all those together in a combination in a fifth dimensional object, those particles would when they go together, they would create so the thing is, like, objects are finite. So for example, this is a three-dimensional object, and it's made out of a certain number of atoms. So if you have a fifth-dimensional object and it's made out of a certain number of branches, it's going to be finite. So you're not going to have an object that's infinitely large. You're not going to have a computer program that's infinitely large inside a computer. So you have to segment the number of computer programs you can have inside a computer, and then once you do that, you can, depending on how much memory your computer has, you can run either all of them or none of them. So there's this thing called a busy beaver problem, the busy beaver problem, whereas they take the number all possible programs to a certain length, and they run them and they see when do they halt. And they've proven that certain programs at a certain length do halt of all possible lengths. So the thing is, they've proven that like for a program that's 5 digits long or 7 digits long, and they've proven whether or not some of them halt or some of them don't halt. And so the thing is that the particles in the universe, they're interacting with each other, and so because they're interacting with each other, they're branching off into different realms with each other. So the thing is that they overlap, and so you have two particles or two networks, and they're expanding and they're expanding and they're expanding until they overlap with each other, and then when something touches that field, like something, see, this is what happens with the measurement problem. People don't understand what the observer is. The observer is not an outside consciousness. The observer is just just a particle touches the bubble of these fields, and then they collapse with each other. So all particles are observers. It doesn't matter what happened. It's just that it's when they overlap, and so when they overlap to a certain extent, when you pop the bubble, it has to collapse. And so the thing is, like, bubbles are coming together, and so eventually the bubble gets too big and it collapses. Eventually the small bubble comes over and it pops the big bubble. And so the thing is, that's all an observer is in quantum physics. It's not some weird new age stuff or anything like that. And so the thing is that Richard Feynman came up with these diagrams for how particles interact, and they're called amplitudes. So the thing is, when you're measuring particles, because of the standard model, when they come together, photons, electrons, and neutrons, and how they come together, there's about 220 ways they can come together and interact with each other. And so the thing is that there's this thing called the amplitude hedron, and the amplitude hedron was invented to simplify this, to say how the bubble expands and how it collapses, depending on the interactions you have with the particles in the standard model. And so the thing is that so the particle wave duality is really very silly, because you don't really have particles, you don't really have waves, you have fluids. And these fluids are influenced by how they overlap with each other. And the way they overlap with each other is dependent on their network structure. So if you were to say that I threw a rock in a pond and it creates a wave, and I throw a long bar in it's going to create a different wave than a short bar will create. And so the thing is that these particles are actually just the little networks that are shaped in different ways, that when they all go together, the field changes. And like I was saying, this field is everything is interacting with itself on the fifth dimensional level. So a particle over here, so if this particle collapses and this particle collapses at the same time, one is up, one is down, and that's an interaction from a distance. And the only reason that they can do that at a distance is because in a higher level they connect. In the higher dimension they connect. And so at the lower dimension they can't go at the speed of light, but at a higher dimension they can flip or whatever. And so Stephen Wolfram is trying to do this. He's trying to figure out how these little networks go together. But the thing is that you cannot calculate 10 to the 99 power amount of particles in a fluid. You can't do that. So the thing is that you have to have these things called probabilities. And these probabilities tell us, okay, so where is the moon going to be in 12 years? We can definitely figure that out because we have a good sense of where the moon's going to be in 12 years. But the thing is that as we get smaller and smaller and smaller, we don't know where things are going to be. We don't know who's going to win the next election. We don't know when the next war is going to start. We don't know a whole bunch of stuff because it's either too big to fit inside our computer or it's too small to... I mean, it's called the uncertainty principle. So the uncertainty principle goes... That's how we found out what the Planck length is because of the uncertainty principle. Now, once we go down to the smallest unit of measurement, the Planck length, we get so uncertain that we can't have anything smaller than that. And so the thing is that when these fields, okay, so an electron is not a particle. When you have an atom, it's vibrating all around the atom in different shapes and combinations. And so the thing is that the electron is a standing wave. And the standing wave goes around itself and around itself and around itself. And so it's just, it's more of a fluid dynamic than it is a particle dynamic. And so the thing is that these particles or fields or whatever is stuff, it's just like space is not empty. It's full of stuff. It's full of stuff and everything is going through it. And as it goes through it, that creates our reality. And so the thing is that like I said that these fluids only have a discrete level within themselves, which is the Planck's length. And so the thing is that when you dark matter and dark energy. Now these things are actually fluids in time. So the thing is that special relativity is a line. General relativity is a cube. And that because there's 5 dimensions, we have to measure things in a different way. So there's not really one dimension of time. There's 3 dimensions of time, and that's a very weird thing to think about. But the thing is that it has to do with how things are moving and how we measure them. So time, even though we feel that time is linear and things are happening now, there's frames of reference. And those frames of reference tell us that as one thing happens here, when we see it over there, it's not going to happen at the same time as as it's happening to us. So if I'm 5 feet away from you, we're pretty much happening at the same time. But if I'm five light years away from you, it's a little bit different, because time slows down and time speeds up because we're moving relative to ourselves and to other things. And so because quantum physics is discrete, there's a limit to how general relativity goes. So if we put general relativity into the fifth dimension, that changes how we have to look at it, because when we look at it from the fifth dimension, like I said, Stephen Hawking said that a singularity does not exist in a black hole. Everything is not, information is not destroyed, and so that means that general relativity has a limit. That means that that's why we had the speed of light. And so the thing is because of dark matter and dark energy do not actually exist. What's happening is our frame of reference is changing so fast that time slows down or speeds up in the fifth dimension. Because time is slowing down and speeding up in the fifth dimension, it only looks like there's extra matter and extra energy. But in reality, everything is in a steady state. In the fifth dimension, everything is a steady state, as Einstein believed, as the cosmological constant. But Einstein was only thinking of the fourth dimension. In the fourth dimension, the cosmological constant does not work, but in the fifth dimension, the cosmological constant does work, because everything is stationary relative to itself. But in our three-dimensional time perspective, in our third dimension, with a one-dimensional time perspective, everything looks like the Big Bang looks like it happened over there, and it seems like everything is speeding away from each other very, very rapidly. But the thing is that that's only from our perspective. From the outside perspective, everything is stationary. It's just that it's like everything is not moving as fast as it should be, because there are no dark matter particles, there are no dark energy particles. So it's all very not like we think it is, because people don't actually do research, and scientists don't actually communicate that well. And so the thing is that I guess the last thing I want to say is that there was a commenter on a forum, and they were thinking about sacred geometry. And so the thing is that sacred geometry works if you believe in feedback loops. So for feedback loop, so resonance. So everything is going back and forth into itself. And so in the fifth dimension, if the universe is a fifth dimensional object, everything is going back into itself. And to us, everything looks like it's speeding away. But in reality, what's happening is that we're slowing down. We're slow. Everything else is we're slowing down, and everything else is stationary. And that's why things seem like they're speeding up, because we're slowing down, not because everything is speeding up, but we're slowing down in the fifth dimension. And so sacred geometry would be just another way of saying, okay, the fluids, when they bounce off of each other, they create these waves, these bubbles, and these bubbles have certain shapes, and those shapes are inside of our inside of our bodies, and so I guess that inside of our bodies we're able to take everything in, and so for example, like our cells, our cells membranes. So if our cell membranes fell apart, it didn't bounce. If everything's bouncing off of each other, why doesn't everything fall apart? And that's because we're feeding back into ourselves and we're regulating. So when it gets too much, slow down. When it gets too slow, speed up. And that's what our bodies do, and that's why we're able to. That's why we're able to not fall apart as biological organisms, and that's why we're able to, I guess, channel entities or do the Chinese thing and qi, yin yang energy and all that stuff because we're regulating ourselves, and we're regulating ourselves because we can detect where the energy goes inside of our bodies, and because we can detect where the energy goes inside of our bodies, we are conduits, and we let things flow through us, and as they flow through us, we learn more, and we're able to do more. And it's just that the chakras, the acupuncture points, and it's all very interesting because we're fluids. We're standing waves. We're fluids that are constantly generating within, and because we're constantly generating within, physics is very complicated, and so the thing is, like, we're energy beings, and as energy beings we're able to be aware of all the fluid energy inside of us, and we're able to project into reality what those particles, or we're able to project into reality the fluid dynamics within ourselves and within, and also the universe.